Hello, everybody. All right. So, in terms of announcements, nothing I haven't already said before. Obviously, the tests number 2 are in your tutorial, your next tutorial, whether that's tomorrow or Monday. And also a reminder that once the tests begin, I no longer really answer questions about it. So if you do have any questions about the test, make sure to ask me today. Either now if you'd like, or after class, or via email. But once the tests begin, I can't be giving information out that people who have already taken the test would then therefore be justifiably upset that why more information was given after their test. All right. Any specific problems you want you to do? Yeah, the recommended questions in the textbook. Is the tutorial same as the... Yes, when I say tutorial, and that's the same thing as the lab, yeah. It's more of a philosophical thing. I think of labs as being like wet labs, like physics, chemistry, stuff like that, even though the system recognizes them as the same thing. To me, it's not really a lab if you're not doing some scientific experiment. Any tips for timing? Try, obviously, ideally, everyone has been doing the practice work. Try some questions without your notes. Try stuff without that, because I find most of the time if people are staring at or using their notes to do problems, stuff like that, even though it's allowed, if people do that, then time runs out very fast. So I would recommend that eventually the transition should be trying to do these questions without any notes or anything. That usually makes it go quicker. Can we start uploading if we finish before the uploading time? That's a new one. Yes. That's been the opposite of the questions I've been typically getting. Since the test covers 1.4 to 1.7, can we expect that there won't be questions specifically about things in 1.1? Yeah. So we're not directly testing anything that comes before. This is for the 5-term test, basically the glorified quizzes. But we still called them term tests, so I'll go with that. We aren't directly testing. So this is different than the midterm or the final exam. But when it comes to the term tests, we're not directly testing earlier material. Of course, math just naturally is. So if if some kind of row reduction shows up on the test, you can't come back to me and say, you did row reduction in 1.1. So yeah, we're not directly testing earlier material. How many questions? 3. The midterm is at 6 p.m. No idea. Whatever the course outline says. Yeah, everyone writes the midterm at the same time, so it's in the course outline as to the date and the time of it. All right, if people have more questions, feel free to fire them off. If not, there's a question right in front of you. Feel free to get started. Did I not just answer that? I just answered that. 3. Oh, I paused it. Boom. See? Magic. Oh, huh, I didn't share it. My apologies. 1 second. There is now a question in front of you. I mean, it's the next one on the slide that was downloadable. So. If this question is too much work, then we need to be a little bit more strategic on how we do it. All right, so this is a determinant. It's a 4x4 determinant, our first foray into 4x4 determinants. And as we discussed a bit on Tuesday, 4x4 determinants in general are nasty. And the reason why 4x4 determinants are nasty in general is because if we do cofactor expansion, what happens? I don't think that's the answer. Yeah, a lot of calculations is certainly a correct answer, but every single minor turns into a 3x3 matrix. So unless something special happens, if we expand along a row or a column, it's a number multiplied by a determinant of a 3x3, and there's not just one number. How many of them do we have if we have a 4x4 matrix? How many of these 3x3 matrices do we get? Yeah. So if we expand along a row or a column, there's 4 entries, and each entry is multiplied by a 3x3. So we end up doing 4 3x3 matrices multiplied by a number added together, which gets a little bit crazy, unless what? So what makes this question much nicer than that? There are a lot of zeros, which means if we are being strategic on which row or column we're using, then it's not so bad because of the sheer number of zeros that we have. Of course, if we don't have any zeros, this gets really difficult, which leads into a second method of finding a determinant that we might see a bit of today, but honestly, we'll probably just see more of next week. All right, anyway, strategy aside, I'm seeing a lot of second rows in this one, so absolutely, we're going to expand along the second row. So we start off with this entry, row 2, column 1, which means we'd be taking, well, is the cofactor going to be the negative of the minor or the positive of the minor? And the answer, it doesn't matter, is not allowed just yet. Yeah, it's going to be the negative of the minor, so I'm going to indicate that by just saying minus 0. Now, technically, that 0 is times some determinant, but because it's a 0, doesn't really matter what that minor is going to be. Then we move on to this 0. Is it going to be plus or minus? I know, seems like a silly question, but yeah, it would be plus. The idea is now that we're at the 3, now it does matter, plus or minus. minus. So the only reason I bothered with looking at it from the beginning was because we could do that alternating thing. If we know where we start, we can just alternate to get to wherever we need to go. All right, eliminate. Whoop, don't literally eliminate the row. Eliminate the row, the column. Beautiful. All right. So, any questions about this? Oh, I forgot about the last zero, plus 0. All right, so we expanded along row 2, and since there was only one of them was a non-zero number, there's only one 3 by 3 determinant that's left for us to handle. All right, any questions about the first step before we move on? Sure, we could use any row, we could use any column. The question is, which one will make the least amount of work for us? So if someone wanted to go along the third row, a third column, we could have done that. We could go along any row. If someone wanted to go along the third row, I don't know why you'd want to, but it works, and it would give you the same answer maybe 5 years from now, but it would end up giving us the same answer. All right, moving on to here. There's a couple options that can handle this determinant, but for example, I think I saw first column. That being said, third row is probably just equivalent in terms of the amount of work. So if we did do first column, that's going to be the 1 times 20, 5, 1, and 18. Minus 5 times 2, 1, 1, and 18. And I'm going to write it out for educational purposes, plus 0 times 2, 1, 20, and 15. Or sorry, not 15, just 5. All right. So here we have our determinants, and we could multiply this through. I'm going to put a little star here because I'm going to come back to this line. But now we just finish the thing off. 1 times anything doesn't matter. 2 times 18, 360 minus 5. This would be what? 36 minus 1 plus 0 times technically negative 10, but doesn't really matter. So this is 355 minus 5 times 35. This is why on tests I lose sleep, spending too much time making the numbers look a little nicer. And we do indeed get negative 540. We'll see after the next few days. All right. All right, so any questions about how we did this and how we can be a little bit more strategic if there are zeros and how we're going to compute these determinants? All right, so I'm going to go back to, so I'm going to ignore the negative 3 for just a second, and I'm going to go back to the 121, the 525, and the 10118. I think that was the matrix we had. Yeah. All right. I'm going to go back to, and I'm going to go back to what I labeled as star for an educational purpose. So we said that just this determinant piece, forget about the negative 3 for just a moment, just this determinant piece was 1 times 25, 118 minus 5 times 2, 1, 1, 18 plus 0 times 2, 1, 20, and 5. So we're going to have a little bit of fun here. We're going to have a little bit of fun, and I'm going to write it out as 20 times 18 minus 5 times 1 minus 5 times 2 times 18 minus 1 times 1. And I'm even going to write this. Minus 1 times 20. So instead of, just actually multiplying, I'm just going to write out the factors. Same thing here, distributive property. Minus 1 times 5 times 1, minus 5 times 2 times 18, plus 5 times 1 times 1, plus 0 times 2 times 5, minus 0 times 1 times 20. Right. Someone was asking about this last class, and I said, stay tuned. All right, so how many of these, technically they're called elementary products, but you don't need to know that word. How many of them do we have? 6. And I put up 4 when I said 6 for some reason, I don't know. All right, so there's 6 of them. Now look at these products and look at this matrix and see if you can see where they come from. Can anyone see where these 6 elementary products are coming from? The second column I see is 2 times 20 times 1, and I don't see that in any of our products. I don't see 2, 20, and 1. Nor do I see 1, 5, and 18 anywhere, no. So one of them is this diagonal. All right, what about the rest of them? What about this diagonal? 0. No, I don't think the third column shows up. I don't see 1 times 3, 5 times 18 anywhere. How about 2 and 5? 2 times 5 shows up times what? Technically 18, but there's a second one. There's also a 0. All right. I should have had 9 different numbers, but it is what it is. What about this 5 times 1? Are we seeing this 5 times 1? I mean, there is a 2 times 5 times 18 as well. Times this 1. In other words, we have one diagonal moving to the right, another diagonal moving to the right, except once you hit the end, you kind of have to loop back to the beginning of the next row. So if I just rewrote the first column here, then we'd have 1 times 20 times 18, 2 times 5 times 0. And if we rewrote the second column, we'd get 1 times 20 times 18, 2 times 5 times 0, and 1 times 5 times 1. Down here, check, check, and check. So the little products are all the same. So we're not really doing anything different, but we can kind of see these, this would be what it looks like. Going down to the right, as we go from the bottom to the right, we can see these elementary products showing up. All right, what about the other 3? And these were all the positive ones. What about the other 3? Can anyone see them in our little, whatever you want to call it? I think basket weaving is the method it's called, but I don't know if anyone weaves baskets anymore. Yeah, if we take a look at the ones going down to the left, 1 times 5 times 1, check. 5 times 2 times 18, check. And 1 times 20 times 0, check again. So the idea is for 3x3s, and I can't stress this enough, 3x3s only. 3x3s only. We have this little interesting way of rewriting the matrix, and we can get these 6 elementary products. The ones going to the right were positive, the ones going to the left were negative, and we can get these elementary products as an alternative way, although as we see here, to get the exact same thing that we would get with cofactor expansion. So this gives you an alternative way, is to kind of rewrite the first 2 columns as the last 2 columns, and then do what's called kind of basket weaving, where you crisscross the bottom down to the right is positive, down to the left. The choice is yours. Personally, to me, I never do it this way, but sometimes students like it, so if you like it, be my guest. Unless the question specifically says, use this method, use a specific method, in which case, do what the question says. Yeah, and so we would get the 3 positive ones, the 3 negative ones, and then you just multiply and add or subtract however you would need to do. We'll do another example of this in a little bit to kind of see it in action. All right, any questions about... I've heard it referred to as basket weaving. I mean, I don't know if that's an official name for the method, but... So this is an alternative way, can't stress this enough. 3x3s only. 3x3s only. You can't use it on 4x4s, it doesn't work. The 4x4s have 24 of these little elementary products, and if you do the basket weaving thing, you only pick up 8 of them. You don't get all 24 if you use this method. I'm not saying it's obvious why there's 24. All right, anyway, if you have any more questions about that, feel free to let me know. If not, give this second question here a try and see if you can figure this one out. What? Did I recopy the exact same one? That stinks. Yeah, but I mean, it's just A transpose, so... It's the same thing. It's a different matrix. Why is it the same? Okay. So every matrix is equal to its transpose. Well, that's good to know. Right. So in the original matrix we did, on the first matrix, we expanded along the first row. Or sorry, second row. What are we going to do now? Right, we could expand along the second column. So we're going to expand along the exact same thing, except it was a row before. Now it's a column, but the idea still stands. Starting off with the 0. Starting off with the 0, is that going to be plus or is it going to be minus? It's going to be minus. Same as it was before. Then plus the 0, then minus the 3. Eliminate the row, eliminate the column. We have 1, 5, 0, 2, 20, and 1, 1, 5, 8, and then plus 0. And we'll notice, because everyone seems to be shouting it out in the chat, which I want people to look for things, that's awesome, is this should be very, very familiar. We got the same 3 zeros as we got before. No surprise there. We got the same -3. Is this the same matrix that we got before? The same matrix? No, it's not the same matrix. Is it related to the matrix that we got before? Absolutely it is. Take a look at that. Bounce back. Well, the matrix is right here. Take a look at this, and we see that they are transposes of each other. Now, these things aren't symmetric, except that should be 18, and so should that. These aren't symmetric, but they are the transpose. So we started off with the transpose of the original matrix, we expanded along the corresponding row or column, and we end up with a 3x3 determinant that's just the transpose of the one we got before. And then we started again. So we did the first column before, so what should we do here? All right, boom. First row, that's 1 times 20, 1, 5, 18, minus 5 times 2, 1, 1, 18, minus, or technically plus 0. And once again, we got the exact same expression we had before, except these two matrices are what? Hard to tell in the second one, but the first one is the transpose. The second one is the same, but that's because it's symmetric. All right. So in this case here, we get 20 times 18, same as we got before, minus 1 times 5, and the only difference there is we're doing 1 times 5 instead of 5 times 1, which changes absolutely nothing. So as some people were saying, nothing changes if we use the transpose, and we get the exact same negative 540 that we got before. So our cofactor expansion, if we're ever doing the transpose, it's not going to change what the determinant is. So call this our first determinant property. The determinant of a transpose is equal to the determinant of the original matrix, which means anything you can do with rows, you can do with columns, because that's what the transpose does. And we'll see that along the way. All right. Any questions about this, either of these two examples or the connection between the two? Correct. The determinant of A transpose is equal to the determinant of A. And we don't even need that it's symmetric to come to that conclusion. Beautiful. All right. Moving on. Give this question here a try. And you should be done. I'll quickly write it out here. Sorry. That being said, the questions are downloadable from UMLearn. All right. The determinant of A can't equal 0? Why can't it equal 0? Great question. If the determinant is 0, what does that mean? Right. So if the determinant is 0, then it means it's not invertible. It doesn't mean the determinant can't be 0. It just means if it's 0, then it's not invertible. Which technically we haven't proven yet. We proved if it was non-zero, then it is invertible. We haven't actually shown the other way around. So you can either take that as a, we'll see about that, or feel free to read a bit ahead in section 2.3 when we will definitively show that. But yeah, that is going to be our connection. But the determinant can still be 0, it just means it's not invertible. Anyway, why is the determinant of this 0? Everyone seemed to jump to 0 right away. Why is this 0? Right, so if we expand along column 2, then it's 0 times something minus 0 times something minus 0 times something. Technically, it starts with a negative, and we get 0. All right, come up with a rule. Come up with a rule. Right. Has a row or column of all zeros. Then the determinant of A is 0. And that, that's just cofactor expansion. Cofactor expansion would say, just expand along that row of zeros. Everything is 0 times something. It turns out to be 0. So I don't know if you necessarily need a property like this to remember that. It's just really just cofactor expansion along the row that has the most zeros. In this case, the row that has all of them. All right. Can you just mention the property without showing them the expand? Yeah. You would just say, and this is part of explaining your answer, the determinant is 0 because it has a column of all zeros. The end. C11 always starts as positive because of the negative 1 to the I plus j. Right? It's negative 1 to the I plus j. So C11 would always be positive because it's negative 1 to the 1 plus 1. Beautiful. All right. Let's keep it rolling. Is there? All right, well, let's try this determinant. And some people might be trying to think of a property, which is great. Some people might be trying to use a property they already know. That's great. I'm going to pretend like we don't know anything. This is just cofactor expansion. I see a lot of zeros. Which row or column should we use? Row 1 sounds good. So if we use row 1, then that's going to be 3 times 2, 0, 0, 3, 8, 0, 0, 5, negative 3, minus 0 plus 0 minus 0. All right. So we have a 3 by 3 determinant. We're going to stick with cofactors. Which row or column should we do? Hint, I'm going to decide for myself whichever one I want. Row 1 sounds good. 3 times 2, 8, 0, 5, negative 3. All right. And how do we get this 2 by 2. Oh, I guess for educational purposes, minus 0 plus 0. How do we do this 2 by 2? I don't want an answer. I want a how. We do AD minus BC, except what do we know about BC? It's 0 because of that 0. And so we get, negative 3. And so we get 3 times 2 times 8 times negative 3, which is whatever it is. Negative 144. All right, so we ended up just multiplying along the diagonal, but we certainly know from every single example we've done before, except for maybe the all 0 row example, that that's not something that always happens. You can't just multiply along the diagonal. It doesn't always work. But this is happening, someone says, because it's an upper triangular matrix. Why, because it's an upper triangular matrix, does this work? Was there really anything special about these numbers, except the zeros? Yeah. Because all of these things were 0, everything else other than that product along the diagonal eventually multiplies by one of those zeros. And maybe more than one. So as we can see, we started with an upper triangular. The only surviving term was still upper triangular. And the only surviving determinant after that stayed upper triangular. So eventually we worked down to just those diagonal entries. All right, property time. If A is, this one was upper triangular, what would happen if it was lower triangular? Would we get the same thing? Yeah. How do we know that? I don't want to do another example. How do we know that if it works for upper, it works for lower? Because the determinant is the same as its transpose. Then the determinant of A is the product. Oh! You're right. My mistake. Our example was lower triangular. Fair enough. Thank you. Yeah, so our example was lower triangular. I don't want to do an example of upper triangular. I got faked out. Yeah, but the idea is if it works for one, it works for the other, because as we've already seen, the determinant is equal to its transpose, so upper and lower triangular would do the same thing. Beautiful. And so we don't even need diagonal for this. Upper or lower triangular is good enough. We don't even need. Now, do be careful. Let's be careful here. Warning. What about this? What about this? Is it 1 times 2 times 4 times 7? Yeah. This is not upper or lower triangular. Upper and lower triangular talk about the main diagonal. The main diagonal is this. That's the main diagonal. So try it. I encourage you to try it and see what happens if you did expand along the first row. In fact, we can probably talk about it briefly right now. What would happen if you expanded along the first row? that would be different than what we had when the 1 was in the first position. What is slightly technically different? It's subtle, but it is different. It's not going to be 0. That 1 is in a place where the cofactor is the negative of the determinant. Now, I'm not saying the whole determinant is negative. I'm saying there's going to be some negatives showing up, because then we would move on to this determinant, and then that one would be negative. Adding in a second negative, leaving us with this determinant, adding in another negative, which would be a third negative. So overall, this one would be the negative of that. But that's because of the particular size. Change the size. 0, 0, 1, 0, 2, 3, or 3, 4, 5. Change the size, and all of a sudden, the number of negatives change. So sometimes for this, what's sometimes called skew diagonal, or sometimes called off diagonal, sometimes it's the same as the product. Sometimes it's the negative of the product, depending on the size. So just as a warning, the property we show that it's the product along the diagonal, you have to be upper or lower triangular, and these would not qualify. It's not to say that the determinant is hard to find, but it's not as immediate as multiplying along that diagonal. All right, any questions about this example or its corresponding property? Yeah, it does sound messy. It is messy. That's why it doesn't become a property. If you want, I can write down a property, but no one's going to remember it anyway. All right. So let's just recall we've done this example. We did it before. And we saw if we expanded along the third row, this is what we got. I want you to give these 3 a try, but for educational purposes, I want you to try expanding along the specific rows that I'm mentioning right here. So give these 3 questions here a try and see if you notice anything when you're doing it in relation to what we had up here. Oh, there's a lot of stuff wrong here. Oh no, third row. My mistake. Sorry, this is, I'm going to rewrite it. Rewrite this thing. I mean, the final answer is right, but not based on what I wrote. Shouldn't change how you find the determinant, though. The matrix that I had on the slide was the thing I circled here. Yeah, the thing I circled here was not right when I was copying and pasting to make my slide. I made some copy paste fails. So that's not right. The corrected version is right here. All right, so let's do this determinant here by expanding along the first row. What do we get? First row is going to be 2 times what? I'm not looking for final numbers, not that it's wrong. I'm looking for the actual 2 by 2 determinant. Yeah, it is negative 18, of course, but it'd be negative 2, 5, 4, negative 1. Minus 0, 3, 5, 2, negative 1. Plus 6, 3, negative 2, 2, 4. Beautiful. All right. Again, we're searching for properties here. We're searching for properties. Look at this and look at what happened in our original matrix. What's the connection? What is the connection there? The rows switched. The rows switched. So we switched, if you look at the original matrices, we flipped 2 of the rows. We flipped 2 of the rows, therefore, if we expand along the appropriate new row, our entries stay the same, but the cofactors have a determinant when the rows are switched. So does the determinant stay the same? No. Because what happens to A, B, C, D if you switch it to C, D, A, B? This one becomes CB minus AD. The original one was AD minus BC. Those aren't the same, but hopefully you can see what are they to each other. What is the connection? They're not equal, but what is the connection between these two if we switch 2 rows? All right, they became negatives. The sign changes. So if one of them was negative, it becomes a positive. If it was positive, it becomes negative. We can kind of see that if we do the calculations. That's going to be 2 times, this is 2 minus 20, whereas up here you would have gotten 20 minus 2. Technically this is 0 anyway, so it doesn't matter, but that one would have been negative. Same thing here, we get 12, minus negative 4. Up here we would have gotten negative 4 minus 12. In other words, we get the exact negative of what we would have had before, making our final answer 60 instead of negative 60. But this isn't some, arithmetic fluke. This is happening because the minors are having switched rows. And hopefully I've convinced you enough that it doesn't really matter what the numbers are, that if we flip the rows, we end up just getting the negatives. All right. Any questions about what happens to the determinant if we flip 2 of the rows? All right, let's try the next one. So what's that? 2, 4, negative 1, 3, negative 2, 5, 1, 0, 3. What would happen here? So again, if we expand it along the first row, what changes? the third row was divided by 2. So we get 1 times minus 0. I shouldn't have put a 0 here, but too late. Plus 3 times 2, 4, 3, negative 2. So when we write this out, what stayed the same? What changed in our determinant? You can still see it up here and down here. What's the difference between these two? So those numbers in front got cut in half. What changed about the cofactors? Absolutely nothing. So if we look at what we had before and we look at what we have now, we've taken row 3 and divided it by 2. That took the numbers and divided it by 2, but it didn't change the cofactor. So what does that do to the determinant? It cuts it in half. So instead of 2 times 20 minus 2, and I guess we could just say that's equal to 18, instead of 2 times 18, we have 1 times 18. Instead of 0 times something, we have 0 times something. Instead of 6 times negative 16, we have 3 times negative 16. So in total, what do we get? We get half of the determinant. So by taking half of that third row, that ends up making the determinant cut in half as well. And again, that's not a coincidence here because we can see that every single number stayed exactly the same. And so the cofactors would stay the same, their coefficients would get cut in half, which with the little factor job would mean that the entire determinant gets cut in half. Or it's just another determinant example and I'm over-explaining things. One or the other. If you want to treat these just like they're just another determinant example, that's perfectly fine. We'll come to some big reveal at the end. All right, the trickiest one, and if you have a question about that, feel free, but the trickiest one is the last one. So 0, 4, negative 7, 3, negative 2, 5, and the last row will keep it the same. So again, expand this thing along that same third row. I mean, we get it from adding 2 times, or subtracting 2 times row 3 from row 1. So note, this is row 1 is row 1 minus 2 times row 3 for this last one. That one's a little harder to see, but or it's just another cofactor expansion practice, however you want to think about it. All right, so if we did it again, so this is 2 times, what is that, 4, negative 7, negative 2, 5. Minus 0 again, plus 6 times 0, 4, 3, negative 2. What do we get for a final answer? we get negative 60. Yeah, so we get negative 60. Weird. So that's a little bit weird. Can anyone see so, I mean, what's the connection between that and the original determinant? Yeah, it seems like this row operation of adding a multiple of one row to the other doesn't seem to change the determinant. Now, that, I mean, unlike the last two where it seemed to be for a decent reason, this one seems to be quite a bit of a fluke. That being said, it's not a fluke. And it is something that's certainly true. All right. Anyway, from the point of view of how we found the determinants, does anyone have any questions about how we found the? Oh, flukes happen all the time. The about how we actually found that determinant. All right. I'm going to try and justify. So this one did. So let me just try and justify this for you a little bit. And again, if you are a little bit annoyed is the wrong word, tired of me explaining properties to you, feel free to just treat this like another determinant example. But here's our original one, our original matrix, and here's our new matrix. So here's our original matrix. And this could be proved using, formulas and this and that. This could be proved using formulas and all these other things. But instead of expanding along row 2 or row 3, I'm going to expand both of these along the second row instead. So this is negative 3 times 4106 plus negative 2 times 2 negative 126, and then minus 5 times 2 420. For this one, the last row stays the same, but the first row changes. All right. So even though things got wonky, let's take a look at this and look at these two determinants. What do you notice about them? BC is still 0. So those determinants are certainly going to be the same. They're both 24. Maybe that was coincidence because of the 0. What about these two? Which one? Which one's 14? Yeah, they're both 14. Same thing if you go here and here. Same deal. And the idea is, it's easier to see from 2 by 2s. The idea is if I take A, B, C, D, and then that's AD minus BC. If I do, say, A minus KC and B minus KD, and keep this the same. So this would be adding a multiple of the second row to the first one. So from here to here, that's row 1 is row 1 minus K row 2. K can be any number, doesn't matter. What happens when we multiply these things together? What do we get? we would get A minus KC times D minus B minus KD times C. That is going to be AD minus some extra ugly term minus BC plus that exact same ugly term, and these things cancel off. And so we're going to put this whole thing together. And of course, in terms of big picture, what am I doing to go from here to all three of these? What are we performing to go from one of these matrices to the other? Right. Specifically, don't forget the word that starts with E. Right. We're performing elementary row operations, and we can tell what that's going to do to the matrix. So, again, in terms of big reveal, if B comes from A, by switching two rows, if B comes from A by switching two rows, what happens to the determinant? This was our first example. What happened to the determinants when we swapped two rows? It turned AD minus BC into its negative. The determinant of B became negative the determinant of A. That was our example that turned negative 60 into 60. That was the switching two rows. If B comes from A, by some row becomes K times row, that row. If we multiply a row by something, what does it do to the determinant? No. I think it was just the fact that my K was a half for this example. Yeah. To go from the first one to the second one, we multiplied row 2 by a half. So the determinant got cut in half. So K was a half in our example. And this, perhaps the most surprising one, if B comes from A, by row I is row I plus some multiple of a different row. Has to be a different row. A multiple times a different row. What does that do to the determinant? Absolutely nothing. Absolutely nothing. But the important thing about this is you're using the elementary row operations. So we've been taking off marks, or at least my markers are supposed to be taking off marks for students who do things like this. Row 3 is 2 row 3 minus 5 row 1. That's not an elementary row operation. And I've gotten in too many arguments over the last week since marks have been returned when marks were lost for doing things. This is not an elementary row operation. So you can't do something like this and apply these rules because none of these rules apply to something silly like that. This has to come from the elementary row operations, or the determinant calculation gets completely screwed up. All right. Any questions about this? I'm going to scroll up right here. All right, so we are technically a tiny bit ahead, but we're going to use row operations to try and find this determinant. So the idea is, the big idea, and this one would not need anything crazy, but the idea is, let's say we had a matrix that didn't have a lot of zeros. The idea is if we, let's say we had a 4x4 matrix that didn't have a lot of zeros, and we didn't want to use cofactor expansion, we can use row operations along with what they do to the determinant. And what can row operations do quite nicely? What can we do with our elementary row operations to pretty much any matrix? We could make zeros. We could even do better than that. We could use our elementary row operations to make a lot of zeros. We could even turn it into what kind of matrix? Maybe I, but we don't even really need to go that far. What was the type of matrix that it was really easy to read off its determinant? We could use row operations to make it triangular and then get the answer right away by multiplying along the diagonal. So that's the general strategy that we can use row operations for. All right, I'm going to give you a couple minutes to give this one a try. Try and do this just using the row operations to make it triangular. And then we'll go over it together. And obviously this could be done with cofactor expansion so you can verify your answer too. All right. So our goal is to make this thing triangular. So what row operation should we start with this 3x3 matrix? And again, my row operations might not be the same as yours, but what elementary row operation would be a good start to make this thing triangular? Switching row 1 and row 3. Now technically I'm going to write equals because we're finding a determinant. A determinant's a number, so we're going to write equals. All right, what does switching two rows do to the determinant? It makes it negative. So that's going to mean our determinant of our new matrix is going to be the negative of the one originally. So performing this row swapping operation is going to make the determinant negative. So we can do that. We just have to keep track of all of the changes to the determinant as we move along. All right. So any questions about that first elementary row operation and its connection to the determinant? All right, what's our next step? I don't want to do that because if I did row 3 minus 2 row 1, this nice, wonderful 0 is not going to stay as a 0. All right. One option, as some people are pointing out, is to just do row 3 minus 2 row 1. You could do that. There's nothing wrong with that. I'm not going to do that because I have an educational reason not to. But that would certainly work. You would certainly get to an answer slightly quicker than the way we will, and there's nothing wrong with that. What other operation could we do to try and kind of replicate our, put things in REF kind of idea? So I'm not saying this is the best thing to do. I'm saying I'm going to do it anyway. All right, so row 2 minus a half. And the reason I'm doing this is because this is the most complicated one, so I want to make sure it's clear how to handle this operation. So this can be a little bit confusing, what I'm about to say. Should this be a half? Is this determinant multiplied by a half equal to this determinant? Are those equal? Not the matrices, but the determinants. Because this is the classic mistake. Oh, I gave away that it was a mistake. This is the classic mistake that happens. So these two are equal? So this and this are equal? No. No. So this isn't a half. This is 2. And that might seem confusing because I just said multiplying a row by a half makes the determinant a half. And that statement is not wrong. That statement is misleading, but it's not incorrect. Because what are we trying to solve for? Are we trying to solve for this determinant? Or in the question, are we trying to solve for the original determinant? We're trying to solve for the original. And the original one is negative 2 times this one. It's kind of like we're trying to solve for the original by getting something at the end. If that's confusing, forget about everything I just said. And personally, I like to think of this as factoring the 2 out of that row. So hopefully that makes a bit more sense. So if we're talking about the determinant, even though this is technically the operation, what we're really doing is factoring the 2 out of that second row. So personally, that's how I think of it. Think of it however you want, which makes the most sense to you. But this would end up being a 2. It would not end up being a half. Again, personally, I like to think, and you'll hear me using this word throughout this next couple sections, factoring the 2 out of that second row. All right. Any questions about that step? Because the other step is more straightforward. And yeah, we could have avoided this by using that operation, but then I would miss a teaching moment. So. All right, row 3, we're out of time. So row 3 is row 3 minus 4, row 2. The negative 2 stays. 1, 2, 3, 0, 1, 2, 0, 0. And 5 minus 8 is negative 3. Now we have a triangular matrix. So how do we find its determinant? Multiply along the diagonal. And we get our final answer of 6. So that means that if we're going to use our row operations, the idea is to turn this into a triangular matrix. You'll notice by the ending here, it didn't need to be in row echelon form. We didn't need the thing to be in row echelon form to do this. We just need it to be in triangular form. And that's what we've managed to accomplish here. All right, if you do it, this was more, we were a tiny bit ahead of the schedule, so the pre-lecture videos explains this a little bit better for 2.2. So, but only by a few minutes. If you have any questions about this, let me know. If not, that's it for today. And good luck on your next test.